Number 48, we've got this image from the spacecraft Galileo. In it, we've got a large asteroid, sort of shaped like a potato, and circled in yellow there is a small asteroid, another asteroid that's actually in orbit around this one. What's going on here? Well, this little small rock is stuck in a gravitational orbit around this larger asteroid. Again, kind of an interesting situation. The advantage of this is we can actually calculate the mass of the asteroid. How can we do that? Well, we know that for things in circular orbits, the centripetal force is provided by the gravitational force. In this case, I'm going to use this equation for the centripetal acceleration, 4 pi squared r over t squared. Why? Because we're given the period, and we do know the radius of orbit, which they say is 100 kilometers from the center of the asteroid. Interestingly enough, notice that the mass of Dactyl, the moon, appears on both sides of these, along with the mass of the asteroid 243 Ida. You can remove the mass of Dactyl from both sides, and then you can actually rearrange the equation to solve for the mass of the larger asteroid. And now we just have to plug in some numbers. So the mass of it's going to be 4 pi squared r cubed over g t squared. Plugging in our numbers, remember that this is 100 kilometers, so it becomes 100,000 meters. It's cubed. Over g times the period, it's 27 hours, and again 3,600 seconds in each hour. Squaring that out gives you that the mass is approximately 6.26 times 10 to the 16th kilograms. Part B says, all right, now we know the mass and we're given the volume over here. What's its density? Well, density is mass over volume, and we already know the mass. But there's one issue I've got to mention real quick here, and that's the volume. It's 14,100 cubic kilometers. Now, you might say, oh, good, I just have to move the decimal place over by a factor of 3 to convert kilometers to meters. But be careful. 1 square kilometer is 1,000 meters cubed. Each kilometer is 1,000. 1 square kilometer would be a kilometer by kilometer by kilometer, or 1,000 meters by 1,000 meters by 1,000 meters, or 10 to the 9th cubic meters. We'd like our density to be in this unit here, so we got to do a little bit of work. The mass from our previous problem is right up here. That just plugs in. And then the volume they gave us in cubic meters goes here, but I'm multiplying by 10 to the 9th because of the fact that we know that each square kilometer is equal to, each cubic kilometer is equal to 10 to the 9th cubic meters. I know it's not proper scientific notation, but that'll be fine. And if you do that, you'll discover that the density of this asteroid is about 4,440 kilometers or kilograms per cubic meter. That's significantly less than the density of the Earth. So this is probably loosely packed conglomerate, probably not solid metal or solid metal like the core of the Earth is. Hopefully this makes sense. Good luck with the rest of your problems. Talk to you soon.